Yeah,
You're gonna be in the office class.
I teach class from right after this one until 2, and then after 2 o'clock. All right, any questions at all about the homework, about anything we covered in class? Question? Nothing? Good. I want to make sure everybody knows that there's an engineering, I guess it's just a grill out right now from 11 till 2 o'clock over in Shelby. They have hamburgers, hot dogs, probably sodas. They have water. I know that. I went over there. There's lunch there. So, without further ado, I'm going to keep going on the stuff, what we were doing. I'm going to put down a few things you'll need to remember. So, first, in general, when we talk about electromagnetic equations, the two things we use to get everything else in terms of equations are Maxwell's equations. We start with curl of H, and that's equal to J plus the partial of D with respect to T. And we start with curl of E is equal to minus dB dt. That's standard. The relationships are J is sigma E, we use that all the time. J is the current density, E is the electric field, and sigma is the conductivity. B is mu H, B is the magnetic field intensity in Webers per meter squared. H is the magnetic field intensity, or magnetic field, and it's in amperes per meter. Mu is just mu relative times mu naught, and it's the permeability. And we also have D is epsilon E. Here E is the electric field, D is the flux density. Now, that's the standard form, the most common form of Maxwell's equations in the SI or MKS system of units. From there, we take it to the phasor domain, so whenever we have time derivatives, they become simply J omega. This is a recap, but I'm making sure everybody knows this. Also, what we usually do is we cast one equation and one unknown. So if you take another curl of this, replace B with mu H and the derivative with J omega, you end up with curl of E is equal to minus J omega mu times sigma plus J omega epsilon times E. Some of you remember doing this. That was where we did another curl of this equation, and then we replaced the curl of H that would occur here with this first equation and the time derivative with the J omega. Does everybody recall this class? I'm going quickly now because I need this to go where I'm going. Everybody with me on this? And if you're missing something, don't worry about it. You can get it after class. This is the standard form. Here, we do one thing. We allow gamma to be equal to, or gamma squared, to J omega mu times sigma plus J omega epsilon. And then, actually, why don't we just make it gamma and make this the square root? And that's equal to alpha plus J beta. Alpha is the attenuation coefficient. Beta is the wave number. Keep going on this. This equation further breaks down to gradient of divergence of E minus del squared of E is equal to, and then it's going to be minus gamma squared E. We make an assumption divergence of E is equal to 0, which means rho V is 0. So it gets rid of that. We have a single equation, del squared of E minus gamma squared of E equals 0. The solutions to this equation are E is equal to E0 times E, call it E0 plus E to the minus gamma Z AX. We assume we're talking about plane wave propagation. Does everybody understand that class? This is last lecture we did this on. You'll remember? This is a wave propagating in the plus C direction, and it only has an orientation in X. That's the AX vector. Just put this plus Z. There's also a possibility of a negative traveling or reflected wave, E to the gamma Z. This would have a positive there, AX. That's what E is. Now, if instead of taking the curl of E, if we took the curl of H and replaced J with sigma E and D with epsilon E and the time derivative with J omega, and we went through that, we would end up with this equation. This one's the lesser that you don't usually talk about. Minus del squared H is equal to 0. These two equations are replicas except E is replaced with H. I'm going quickly, but this is review. You all with me on this class? That would be absolutely true. The solution to this equation would be H here would be equal to H naught plus times e to the minus gamma z ay, and it would be plus H0 minus times e to the gamma z a y. That would be in the y direction, not x direction. Now, when you replace, remember what eta was. Eta, or by definition, E naught plus over H naught plus is equal to eta, which is equal to the square root of j omega mu over sigma plus j omega epsilon. Let me see if I can get another marker. This one is stuck in the diagram. That's sigma plus j omega epsilon right there. That's the ratio of E plus to H plus. But the ratio of E naught minus to H naught minus is equal to minus that. It's minus eta, or it's equal to minus square root of j omega mu times sigma plus j omega epsilon. Have to know that. And furthermore, you can take this H equation and put it in terms of E and eta, and that's what I'm about to do next. I didn't do that last time. I can say that H therefore is equal to E naught plus divided by eta times e to the minus gamma z ay, plus actually becomes minus. This is important. That's a minus sign. Minus E naught minus over eta times e to the gamma z a y. Now we have electric field and magnetic field expressions for propagating waves. This is only for propagating waves in free space, propagating in the z direction, oriented in the x for E and the y for h. Everybody with me? Recap. Now it brings us up to speed where we are today. Now, next thing we're going to talk about, oh, I didn't put this down. I went through phase velocity, wavelength, and period. All right? Just for the record, phase velocity. Let me put that up here because we're going to be using that a lot. Phase velocity is equal to omega divided by beta. That's generally true always. And when we talk about wavelength, wavelength is always 2 pi divided by beta. Those are things that they never change for a constant frequency waveform. All right, so you have to have a sinusoidally or cosinusoidally varying waveform, and it has to be on for a long time. Now, with that, once we have that, now we move into, first, the case, here's what I'm going to do. This is the general form of the equations, right? Here's the H field, right there. Where did I do it? This is the general form for the E field, right? For a propagating wave. That's the general form of the H field. Those are true generally. Doesn't matter if you're going through a good conductor, a low loss dielectric, or free space, right? Those are always true. Now we get into specific cases. So from that, we break it out. The first thing we say is if we have a lossless region of space. Now, lossless region of space means sigma equals 0, and something you can also put down as epsilon double prime equals 0 that I'll get to. It means there's no attenuation energy-wise of the wave or power-wise. It's going to have, there's nothing to dissipate the strength of the signal. Follow me? So the wave keeps propagating. Now when we have low loss cases, first thing we look at is the propagation constant. Well, in general, the propagation constant is j omega mu times sigma plus j omega epsilon, and that's equal to alpha plus j beta. Correct, class? Everybody got that? Now you got to know that. Follow me? Can you all see it in the back? All right, now we do this. I said that if it's low loss, sigma 0, right? So make sigma 0. What do you see happening? I have j omega times j omega or j omega squared. I have mu times epsilon, right? So this becomes gamma is equal to simply j omega square root of j omega squared is j omega times the square root of mu epsilon. You can see here, and I meant that, I said that last time, here, because everything has a j in front of it, right? There is no alpha, so you can put down alpha is 0, also implies it's lossless. Got that, everyone? Alpha 0 means it's lossless. It's important that you see that. Also, when we do this, you can see that since gamma is equal to alpha plus j beta, beta for this case is simply equal to omega times square root of mu epsilon. Agreed, everyone? This is a lossless case. Can you all see it? All right. And for the lossless case, then you get the phase velocity from the fundamental definition. It's omega over beta. Well, if I take omega divided by that, I have 1 over the square root of mu epsilon that we talked about last time. Just to accent this point, what happens if you're in free space? You get c, or the velocity of energy in a vacuum or free space is equal to what? 1 over the square root of mu naught epsilon naught. And what is c, class? About? 3 times 10 to the 8, you know that. 10 to the 8 meters per second. How fast is that in terms of some? Huh? Very fast. Yeah, that's a good way. It's the fastest thing there is, basically, right? Nothing moves fast. No energy or no mass moves faster than that we know of. Now, the thing is, get a reference for this. How many times around the Earth would you have to go in 1 second 300 million meters?
Like
7 times around the Earth in a second. If you've ever been on a plane and looked at the horizon, the curvature, you know that's a long way. That's in a second. You got to have reference for how fast this is. How long, though, does it take photons or electromagnetic energy from the sun's surface to reach the Earth?
8.5 minutes something?
About 8 minutes plus change. So that gives you an idea how far away the sun is. Long way. All right, and you really want to think about distance. Think about how far Pluto is when it's at its maximum range from the sun. And that's why when they send these things like Voyager and stuff out there, they don't wait days or months. They wait tens of years for the thing to get there. And it's going 25,000 miles an hour. That's a long, long way ahead. And it gives you reference. What's the closest star?
5 light years or something?
Well, I think it's a little more than that. But I think it's a little more. You can Google that while I'm here. That's a light year is how long light travels in 1 year. I think about this. It's so far I'm never going to worry about getting. Well, their plans people have, you know, they're scientists that are dreamers, and they probably going to get it done. They're going to orbit something around one of these near stars at some point because of all sorts of new engines, thruster engines. They're coming up. Speculation now, but nevertheless, if you can go as fast, approach the speed of light, then you'll get there, I don't know, by the 5th or 6th generation from you, something like that. Anyway, that's the phase velocity in free space. Make sure you know that. Now, what's wavelength? Just to be careful, wavelength from over there is 2 pi over beta, right? And that's 2 pi over beta. Well, beta is omega, and omega is 2 pi f, right? It's omega times square root of mu epsilon, correct, class? You'll notice 2 pi's cancel, and I have 1 over f square root of mu epsilon, or really the phase velocity over frequency is wavelength. And in free space, it's c over f is wavelength. Everybody got that? A recap. All right. Now, oh yeah. One last thing with low loss region, or lossless region. What is eta? Eta is the square root of j omega mu over sigma plus j omega epsilon, or it is, if sigma 0, it is square root of mu over epsilon. Correct, class? With me? And in free space, what is it? It's just square root of mu naught over epsilon naught, right? And what is that number? Come on, what? 120 pi ohms, right? 120 pi ohms, or about 377 ohms. What's the nearest star you're looking at?
4.22.
4.22, okay. I thought it was further. I was wrong. Long way.
Professor, next to the sigma under lossless region, is that a C double prime?
What's there? Here or up there?
Under region, right under region.
That's epsilon double prime. I'm going to get to that. We haven't got there yet. All right, so that's it for a lossless region. We could do problems, they're not gonna amount to much. Somebody asked me a problem about a lossless region problem, didn't you? Who asked me about the H field? Where are you? There you are, you asked me about it, right? That was problem 34, what was it? Or
6.11.
All right. That problem breaks down using these, everything falls apart. Just use these formulas. There's nothing about it that's hard. Next thing we do, now we do low loss. And before we do low loss, I have to talk about complex permittivity. So this is new. I'm going to slow down here. I want you to be very attentive to what I'm about to show you here. And let me tell you right now, the reason we do this is because of this. Normally we say the curl of H is equal to sigma E, and that is J, plus J omega epsilon times E. All right, and this is real current here. This is called displacement current. Now, what I mean by that, or displacement current density, if you want exact. Real current, J, means real charge is moving through the lattice in an unbound fashion if there's something with conductivity. For instance, if you have a chunk of carbon and you put an electrical potential difference between the two ends of the carbon, an electron will actually propagate through there. All right? If you could paint the electron, you could watch the thing propagate through there and circulate. All right? However, this is displacement current density. Now, that is not real current by any change. If you take a capacitor plate and you put a time-varying voltage on there, current flows in that capacitor. Do you all agree? That current is caused by a displaced charge. What happens is positive charge accumulates on one side, negative on the other, but there is no charge movement through the actual material, or ideally at least, the actual dielectric or insulator. Follow me in this class? That is a displacement current density. Now, propagating electromagnetic fields don't displace charge in general in a lossless region. They can in a lossy region. But now we're getting into something where we have a dielectric that's called a low loss dielectric. Now follow me on this. Yes, sir?
In that formula, what is the del of H is equal to what is?
Curl of H is sigma times E. This is
Okay,
just
sigma.
sigma times E plus J omega epsilon E. It's the time varying form, the phasor form of the Maxwell's Ampere's law. All right? Now, this is the thing. When we talk about things with bound charge in them, think about this. Think of a dielectric that has balls of charge in it. When I put a voltage across the capacitor plates, if that dielectric is in there, these balls of charge will be displaced a small distance. They'll be attractive, if they're positive charge, attracted to the negative plate, right? Repelled from the positive plate. Follow me on this? And they do this. They move back and forth, but they have a limited range. They can't move between the plates. They just bounce back and forth. But they also, because they're moving in a lattice, cause the lattice to heat up and lose energy. In other words, you'll lose energy by heating the lattice. Follow me on this, class? That's called a loss due to what he calls it is he uses a complex permittivity, but it's due to the bound charge. It's really, there's more to this, but it's material science terminology. For now, understand that anytime I have an epsilon double prime, it has to do with loss for bound charge. And now we get into what I mean by that. So when we talk about a lossy permittivity, a low loss displacement current density, or a complex, write this down, complex permittivity, what I mean is this. Now epsilon becomes complex. Put a little hat over it. It's usually a hat, but it can be anything. And that's equal to epsilon prime. And that's the old, just write a little note to yourself. That's just epsilon r, epsilon naught. That's our good old friends, epsilon naught, epsilon r. But then they put minus j epsilon double prime. Epsilon double prime is due to the actual thermal heating or loss mechanisms of the bound charge moving. Now this is important to understand. That bound charge cannot move from one plate to another, so it is different than conduction current related to sigma. Understand? That's the reason we do this. So what we do is, when we talk about complex permittivity and the low loss displacement current case, we take this equation, curl of H, and I do this, I say sigma equals 0. There is no free charge to move. Now Wentworth's book doesn't do it quite this way, but it's almost always this case, so just go with me on this. Curl of H is 0. So that means I have J omega times epsilon complex times E. Now I replaced epsilon with epsilon complex. Follow me? Now I say that curl of H is equal to J omega, and here I replace epsilon complex here with epsilon prime minus J epsilon double prime times E. And therefore curl of H is equal to J omega epsilon prime times E. And then J times J is going to be minus 1, where the minus is plus 1, plus omega epsilon double prime. I'm going to stop there. Y'all see what I'm doing here? Keep it. Are you following me on this one? You might wonder why we have that minus J epsilon double prime. It's a convention that's used. It's been adapted. If you really want to know where it comes from, don't write this down. I'll give you a sidebar on this just so you know this. Long ago, when people were fashioning ways to describe the region behavior, they noticed that curl of H was sigma plus J omega epsilon times E. Are you with me? You don't need to know this, but I'm doing this for your own good. Follow me on this? That's generally true. Then they factored out a J omega. So they have curl of H. This is called Jm. It's the Maxwell current density, but don't worry about that right now. And so they took a J omega out in front. When you take a J omega out in front, you have to divide everything by J omega, right? So then they got, divide this by J omega, they got epsilon, just epsilon. And they have minus, because 1 over J is minus J, minus J sigma over omega times E. Y'all see what I've done there? Just divide this by J omega. I've got sigma over J omega, right? 1 over J is minus J, so I have sigma over omega times minus J plus epsilon, right? And then they said, well, we'll call this epsilon double prime. Now, the truth is, this sigma that is associated with that isn't really a sigma that is associated with charge being able to freely move. It's bound charge. It's a sigma associated with bound charge. And that's where this convention of the minus J epsilon double prime came from. Follow me? Got to tell you one other thing. Epsilon double prime is a strong function of frequency. It varies widely all over the place. Epsilon prime is a function of frequency, but not nearly as strong as epsilon double prime, the loss mechanism. If you want to know a good way to think about loss, have you ever put a ceramic plate in the microwave and heat it and it heats up and you touch it and burn your hand? Well, that charge is not free to move, all right? That's bound charge that is wobbling back and forth at the microwave frequency, and it heats the lattice there, heats it up. And that's how come that happens. So that's an example of something where you have a low loss dielectric behavior. Now, in this one, do this. Circle that, and that's loss. And this is non-loss or displaced current. So that's the loss right here. And what they usually do when we talk about this, we do a graph. What we do is put the loss on this axis, so we put sigma, omega, I'm sorry, not sigma, but omega epsilon double prime E here. That's this, the loss, and on this axis we put J omega epsilon prime, this is epsilon double prime, times E. Now when we graph that, we're going to get something like this, where this would be the loss, and this would be the displaced current. This angle here is given the symbol, that symbol. All right? And it's a delta. Now I got to tell you this much. The thing you have to remember about this is, this gives you an idea of the goodness of a dielectric. If this is the hands of a clock, when it's at 12, it's a great dielectric. There's no loss. The further that hand wobbles from 12, the worse it gets. Do you follow me in this class? And the way they gauge that is with something called the loss tangent. If they wanted to find this angle, they would say the tangent of that angle delta, is equal to really the opposite, which would be equal to omega epsilon double prime divided by the adjacent, which is omega epsilon prime. Or it's simply epsilon double prime divided by epsilon prime. And this is called the loss tangent. And it's the figure of, I use the word goodness, of how well a dielectric is performing. Remember, in engineering, we always have figures of merit. And that's the way we identify how well something is performing its job relative to others. And this is the way we always do it. So the lower the value of that loss tan, the better it is. By the way, isn't the tangent of a small number about that number? Tangent of x is about x, right? In the radius, if it's x is small. And when you do this, generally speaking, for good dielectrics, they just take a look at this, the loss, they'll just have the angle instead of the tangent. But that's called the loss tangent. You follow me in this class? You'll see how it applies in a little bit. Now, with complex permittivities, Stu Wentworth's book has a thing about how to get an approximation if you have a low loss case for alpha and for beta. All right? I prefer, if you want to know what alpha and beta are, you do it the good old-fashioned way. You simply do this. You got calculators. So back in the old day, when calculators were really not that widely used, like when, I don't know, Dr. Wentworth's father was a boy, something like that, about that far back in time, literally. You didn't have it, but this is equal to the square root of j omega mu, right? Now, if sigma is 0, you don't put the next part, right? But now epsilon's complex, so then you put in times j omega, and then it's going to be epsilon double prime, which is epsilon prime minus j epsilon double prime. Now you'll notice that when you do this, I got j times j, which becomes minus 1, right? I got minus 1 times omega squared mu epsilon. Then I have j times j is minus 1 with a minus is plus 1. Then I have omega epsilon double prime times j omega mu, right? Follow me? Now, when you take the real and imaginary part of this expression, you're going to get alpha plus j beta. The imaginary portion is beta, the real portion is alpha, and that's the easiest way to do that. You don't need to do these numerical approximations using really binomial expansion. It's easier to just go on your calculator. Follow me, class? I'm trying to give you a piece of advice. Your calculators will do this in a heartbeat. Don't bother Baginski's interpretation. If Dr. Wentworth wants you to do it, then do it. Don't bother doing those crazy approximations. This gets it every time, and it's easy to do. You got a calculator that can do this. How many have TI-89s? What else you got? TI-84? TI-83? Inspire? Is that a good one?
Yeah.
Right. Isn't there a TI-92 or 91 or something, 93? Anybody got a TI above an 89? I think there is one, by the way. But
I think that's what Inspires are.
Is that what it is?
Yeah.
It's a TI product?
Yeah, it's a TI product.
All right, it's probably renamed it to that. Anyway, those calculators all do these things effortlessly. So I don't need to worry about showing you approximations. All right. Now, next part is important. It's good conductors. And this is the one that a lot of times people don't appreciate when they get to hurt themselves. So I got to erase this. I know a lot of this is dry theory right now. We're going to apply it as soon as I get done with this. Is it supposed to rain today? Does anybody know?
Did you see the class is full?
No? Good.
His special projects class is full. I emailed him about it. I think they only have like 4 seats. The special projects are actually a class. I think just meet in it bigger. Why does it have it in the?
All right.
There's a chance of running at 4 and 6.
Okay. Alabama, I learned one thing. Summer months, it doesn't matter what it says. Take your umbrella. I've seen with a 0% chance,
Well, it's raining.
just pouring down rain on a golf course. It's like, kill the weather. Everybody's. All right. Now we're getting into the case of lossy conductors. This is the one that's important. Most of the stuff, low loss, lossless, it's all the standard base. This isn't. Now we're going to get, this is going to be a good conductor. Good conductor means when you look at it, sigma is much, much greater than omega epsilon. And here's what I mean, why do that? When I have curl of H, remember the sigma E here is the actual current density. That's real current, that's J right there, right? Current density. Plus J omega epsilon E. This is displacement current, right? Well, if you look at this, you can factor out the sigma and the J omega epsilon and multiply it by E. Now for a good conductor, this sigma is much, much greater than this omega epsilon. So that becomes important. Got it, class? This is important. Now when you look at the things like, we start with eta. Eta is equal to the square root of J omega mu over sigma plus J omega epsilon. But the condition was that J omega epsilon was small compared to sigma. Can you all see it, or do I need to write higher? In the back, can you guys see it? If you can't see it, yell. So what I do is just get rid of this thing. Now, I need to make you aware of something that's important. When I have J, that's equal to the square root of -1, typically, right? That's one way of thinking about it. It's also equal to, more correctly stated as e to the j pi over 2 or e to the j 90 degrees. Either of those two is right. You all agree with that? They're all the same. Now, if I have this, really what I have is the square root of e to the j pi over 2 times omega mu over sigma. And e to the j pi over 2, if you take the square root of that, it's the square root of 45 degrees. J to the 45, or j to the 90 degrees. E to the j 90 degrees square root of is e to the j 45 degrees. So this is really e to the j 45 degrees, or pi over 4, times the square root of omega mu over sigma. And that's as good as you need be. It just means that now eta has an angle associated with it. It's 45 degrees. And that's important. Got it, everyone? Remember, we're in the phasor domain, so we have real and imaginary numbers all over the place. And we have angles. That's the intrinsic impedance. Next, when you look at gamma, what do you get? Well, I get the square root of j omega mu times sigma plus j omega epsilon generally, right? But the condition for a good conductor was this, that sigma was much, much greater than omega epsilon. Correct, class? Everybody follow me on this? That means, what can I do? Well, I get rid of this. Right? You all agree with that? I'm just getting rid of it. I'm getting rid of the j omega epsilon because it's now really not a problem. It has no bearing. Now, when I do this, when I have the square root of j, put it here. Square root of j is either e to the j pi over 4, or it's e to the j 45 degrees, or it's equal to cosine of 45 degrees plus j sine of 45 degrees. And in all cases, this part is just equal to 1 over the square root of 2 plus j1 over the square root of 2, isn't it? Sine and cosine of 45 are 1 over square root of 2. Correct, class? Everybody with me on that? Now, if you got that, and you look here at gamma, and I replace that j with 1 plus j times the square root of 2, I have this. I have this. I have square root of j. I'll break that out in front. Then I have the square root of omega. And we're going to make omega 2 pi f times mu sigma. Take a look at that. I broke out the j by itself, square root of j, and I have square root of 2 pi f mu sigma. Y'all agree with me? But what is j? Well, j is 1 square root of j. Square root of j is 1 plus j over the square root of 2. So then I do this. I'll take this and multiply it by 1 plus j, and I'll move the square root of 2 here, so it's just divided by 2. Put the square root operator there. Do you all see what I'm doing? Class, follow me? Can you all see it in the back there? All right, now, why did I do that? Well, because these 2's will cancel. That's the reason. And then I'm left with this. I'm left with 1 plus j times the square root of pi f mu sigma. And here, that's equal to alpha plus j beta, but it means that alpha is equal to beta in magnitude, and it's equal to the square root of pi f mu sigma. And that's important. So in a good conductor, alpha is equal to beta is equal to the square root of pi f mu sigma. Follow me, everyone? I know until you apply these formulas to many problems, it's still just kind of boring, black. It's really sort of math that's cumbersome, but important. You'll apply it to problems in a second. Got it? That's one part of it. So now we've got beta and alpha and the propagation constant. We've got the intrinsic impedance. And there's one other thing we're about to get when we do this. Now, we're going to get the phase velocity. What's phase velocity in its most fundamental form? Class, look over there.
Omega over beta.
Omega over beta. Let's keep going. I'm going to put omega as 2 pi f. I hope everybody knows that. Right? Omega is 2 pi f, where f's the frequency in hertz. Then I go ahead and I put down beta, and that's equal to the square root of pi f mu sigma. Right? Now look what happens. This is really what? Square root of, I can just leave the 2 alone for now. It's 2 times square root of pi squared f squared, right? Over pi f mu sigma. Or I can say the phase velocity here is simply equal to 2 times square root of pi f over, and then it's going to be mu sigma. Y'all agree with me? That's phase velocity in a good conductor. I'm about to show you something. Now, with that, we're going to take some typical values for copper. Hear me? Copper. For copper, mu is about 4 pi times 10 to the minus 7. Units are henries per meter. For copper, sigma is about 5.8 times 10 to the 7th, 1 over ohm meters, or Siemens. All right, that's typical. I'm going to do this at a frequency of make it 10,000 hertz. So 10,000 hertz. Let's take a look at the velocity. What's the phase velocity going to be? And this is copper. At that frequency, at this frequency. What do you get the phase velocity being? Well, it's equal to 2 times square root of pi times 10 to the 4th divided by mu, which is 4 pi times 10 to the minus 7th times 5.8 times 10 to the 7th. The thing you'll notice right about this is the 10 to the 7th and 10 to the minus 7th cancel. The pi's cancel. So I have 10 to the 4th divided by 4 times 5.8, roughly 4 times 6, right? Roughly. Call it what?
The 2 and the 4 should cancel out though.
Yeah, that cancels.
Make it easier.
Why don't we cancel that now? Thank you. What do we end up with? We got what? Square root of 10 to the 4th divided by, or 100, divided by 5.8. So that's going to be 100 divided by square root of 5.8. That's meters per second. Just think about that. That's less than what? Less than 30 meters a second, Rob. I think it's about that, isn't it? If you do it. All right, 30 meters a second. Light was going 3 times 10 to the 8th meters per second in free space. Now it's down to 30 meters per second or so, under 100 meters per second, which is trivially slow. As a matter of fact, if I made that frequency about 100 hertz, you'd be able to outrun the velocity of light in copper. Follow me on that? But that's not this is where you can have a problem. That's not how fast the wave propagates at the surface copper-air boundary. Like when you have a telegraph wires, that goes at the speed of light virtually. This is the rate that energy goes in towards the center of the copper wire. All right? And that's a big difference. So don't be misled to think that, well, signals propagate very slow in conductors. No, they propagate at the interface of copper air. That becomes not really a waveguide, but it's called a boundary region where the wave propagates. And now we're getting there in a second. I'm not there yet, but I'm about to be. So now what we talk about is propagation in good conductors. And what really happens when I have a wire or something made of copper, and we're looking at the phenomena of what goes on. And then for that, I'm going to get this a new board for this part. I'll erase this. Did you have propagation in good conductors in physics or not? Do you remember? I think it depends on the author of the book, because some probably will, and some won't. Advanced physics will. I'm not going to do every proof in Wentworth's book, or everything that needs to be proved, but I try to do the important things. So next, we take a look at what happens in copper. I mean good conductors. I keep throwing copper out because it's one of the most common ones used. Copper, aluminum, really steel. Gold's used, but it's specialty. So now what we're going to do is take a look at what the skin depth really means. When we have a piece of copper, and I'm trying to draw a rod there, and we have a rod with radius A, it's all made of some good conductor, good sigma, all right? Solid. And it's got a certain length to it. And suppose this surface is metallized. I take it and I put some sort of a battery here, plus or minus V. And down here is the end. So it's got a certain length and a constant cross-section. If you look at that, the cross-sectional area A would be pi A squared. Do y'all agree with that? Now here's what goes on. When I put a battery across there, there's an electric field on the surface of the wire, right there, E. And E will be equal to V divided by L. It'll be uniform and constant on the surface of that wire. But towards the center of the wire, here's what happens. What happens is that this electromagnetic field would be moving at the center. If you look right down the barrel of that wire, you would have electromagnetic energy trying to move in towards the center. You can imagine that. That's how the waves propagate. Can you understand that, class? Remember, the electric field's set up on the outside, right? But it would want to propagate into the inside or map into the inside. It's another way of thinking of it. Now, pay attention to this. It'll only go about one skin depth in. I could solve this equation, the exact equation. So really what happens is this. You have basically a region, one skin depth thick, where all the current will flow. That's where the thing basically dies, and here's why. Because if you plot versus Z, and this is going to be E naught times E to the minus gamma Z, which is equal to E naught E to the minus alpha Z times E to the minus J beta Z. Well, E to the minus J beta Z is just a phase, right? When you take a look at this and do the magnitude of it, on this axis, you get this. And you get a point here, and that's called the skin depth. And that skin depth is equal to 1 over the square root of pi f mu sigma. And the way I get that is I know this envelope here is E naught e to the minus alpha z. Well, when it's one skin depth, it's E naught, this point right here will be E naught, when you're one skin depth in, e to the minus alpha times the skin depth, and that happens to be equal to E naught times e to the minus alpha, or e to the minus 1, pardon me. So this is the point when I have 0.33, about 0.33 E naught. That's e to the minus 1. So the way they get skin depth is simply taking alpha and taking 1 over it. And this is called the skin depth. And it's the region where the electric field, it's actually 37, pardon. It decays to about 37% of its max value. Now here's the reason it's so important. Because if you just say, without me proving this, if you just say that all the current is confined to one skin depth, right there, you get an exact answer for the resistance of that wire. It's perfect. And I'm gonna run out of time to prove it today because I only got 2 minutes. But it's a very simple proof to do where you take the integral of this and get a value. I'll get that later. Now getting back to this problem. Just let me finish this problem right here before you leave. Listen to me. When I look at this, well, what's the resistance of wire of a given length or a given cross section? Well, that's the DC resistance. Write this down. Resistance DC is proportional to the length of the wire, right? That makes sense. The longer the wire, it should be more resistance. And it's inversely proportional to the cross-sectional area. That makes sense as well, if it's constant cross-section. The fatter the wire, the less resistance to current. And it's also inversely proportional to the conductivity. For our specific case, it's L over sigma times pi a squared. Now that's RDC for a standard round or circularly conducting wire. When we talk about the AC resistance, write this down, AC or high frequency resistance, then first we assume the skin depth here is going to be less than A. This is the first condition. This has to be true or throw everything out. If the skin depth is greater than an A, default to the DC resistance. Understand? Because skin depth is proportional to 1 over F. But if this is true, if the skin depth is less than A, then you can say that the area, not the conductivity or length change, just the area that the current flows through, that area will be equal to pi A squared. That's the entire area of this. Can you all see this? But then I subtract off this inner area. And that area is going to be pi times the radius out to A minus the skin depth. So I take minus A minus the skin depth squared. Are you with me? Now when you go ahead and turn the crank on that, you get A is equal to pi times 2A skin depth minus delta squared. I'm just doing it because I don't have time. That's what you get. I want to make sure you understand something. Almost always for this one, if skin depth is much less than A, you can say the cross-sectional area is just 2 pi A skin depth. Write that down, and let me explain that. Most of the time, when you deal with these kind of problems with wires and you're at a high frequency, the skin depth is tenths or less of the actual radius. That means what you can do is just break that in the middle and draw it out. And now you have something with a length of 2 pi A and a width of delta, or the area would be 2 pi A times skin depth. Follow me? Y'all with me on that, class? Everybody see that? And that means you can reduce this formula, replace that A with 2 pi A times skin depth. I didn't have a chance to get to the power. We're going to pick it up with power next time. On Monday, I'm going to do some homework. See you. Did y'all understand it today? Did you hear me okay back there and see it?